Alright, trig class, a very natural continuation of what we were just doing in the last video. We were multiplying two different complex numbers together. And how did we do it? We multiplied the magnitudes together, and then we added the arguments. We rotated by those two angles being added together. Well, now the natural thing to do is to multiply a number by itself, or squaring, or raising to a power. And the way we do that is the exact same way. We want to raise a complex number to a power. We multiply the magnitude by itself that many times. And since all the angles are going to be, all the arguments are going to be the same, we just multiply the argument that many times. Because it would be, theta plus theta plus theta plus theta. That's how we rotate, or that's how we multiply the argument part together. We rotate by adding the angles. So we just add the angle together this many times. Okay, this is called DeMoivre's theorem, and it literally deals with how to raise these complex numbers to powers within their polar form. Alright, and then if we used Euler's formula, still the same thing. For Euler's formula is the magnitude to the nth power, but then it's just e to the I n theta. So remember, with Euler's formula, it's e to the I theta. It's just theta was the angle, and now our angle is n times theta. So we have that n theta in there. Alright, let's use DeMoivre's theorem. We're going to take this number to the 7th power. Okay, now what do we need to do before we can do this? We need to evaluate the magnitude. So if we look at the square root of 3 squared is 3, right? Plus the square root of 1, this is 1i, so the square root of 1 squared is 1. And we take the square root, we've got our magnitude. So 3 plus 1 is 4, the square root of that is 2. So our magnitude is 2. Alright, and then the tangent of theta is equal to the part right here, the b divided by a, so negative 1 over the square root of 3. Alright, so that's fourth quadrant, right? Because we're going right, and then we're going down. Right, because of the square root of 3, down the negative I. So this is quadrant 4. So we're looking for what makes tangent equal to 1 over the square root of 3 down here in quadrant 4, right? So that's going to be negative pi over 6. Right? Or you can think of it as 11 pi over 6. Either way is okay here. But that's the angle that we're starting with. Okay, so the big thing to keep in mind as we go through this, the magnitude that we started off with is 2, and this was our argument that we started off with, our original number. So when we start to do the work, we're going to have that's the magnitude of this is 2, right? And then there's negative pi over 6 as our argument. So how do we work through this? Well, 2 to the 7th is 128. And then how did I get this? How did I get the negative 7 pi over 6? That's what we had before. We are raising it to the 7th power, so that's my n. And I multiply. Remember, this is all multiplication. So we can multiply in anywhere we want to. So this 7 is just being multiplied by the pi over 6, and it's negative. Alright, and then just on a unit circle, if you look on your unit circle, so there is, if you look, this is pi, this is 5 pi over 6, and this is 7 pi over 6. But if we're going back the other way because of the negative, that means we're coming in this direction. This would be negative 7 pi over 6. It would be the same place as 5 pi over 6. So when that's the case, again, it's easiest in simplest form if we reduce the amount of negatives. And so if we would end up at the same place with positive 5 pi over 6 as we would as negative 7 pi over 6, then that's a simpler form. So we would write this as e to the I 5 pi over 6, just to make it a less negatives, just simplification, just like in algebra. And then likewise, if I wanted to do in the polar form instead of the Euler's formula here, I could just take that 128, and then this is the angle that goes inside the cosine and sine. So either way you want to do it is fine. They're equivalent. They're identical. All right, and then likewise, if I want to reverse the process, just like we did with multiplication and division. If we want to talk about roots, roots are the inverse operation of raising something to a power. So what did I do before? I raised this to the n power, or now I'm taking the nth root of the magnitude. All right, and now this is the part that's a little bit different. But we are dividing by n. Okay, we are dividing by n, but it also has this little piece to it, and this is using the fact that if I start at an angle and I add 2 pi, and k is some counting like 0, 1, 2, 3 up to n minus 1, n of these roots. If I start with 0 and I add 2 pi over and over and over again, I'm going to land back where I started. But when I'm dividing it by n, which is what we're doing here, notice what we end up with if you break this apart. You end up with theta over n. That's like a starting angle, plus 2k pi over n. And I'll write it like this, 2k pi over n. And this part is rotation off of that. So we start off with the starting angle, and then we're going to, let me write it this way. I think it would be easier to see. If I did theta over n plus 2 pi over n times k times. So this is our starting angle, and then this is how much we rotate every time we go from k equals 0 to k equals 1. So, when k equals 0, it's just theta over n. When k equals 1, we add 2 pi over n one time to this. When k equals 2, we add it a second time. So this will be rotation from our starting angle. All right, and then this is the form in Euler's formula. So let's do one. I think doing one, you'll actually see what I mean by this. All right, so we need to find all the fifth roots of 1. So first of all, remember 1 is over here. Okay, on the real plane, this is imaginary. All right, and these are the reals, right? So the number 1 is just on the real plane. It is literally, if I wrote it in the polar form, it would be z equals, the magnitude is 1 times the cosine of 0 plus I times the sine of 0. All right, those are zeros, not thetas, sorry, 0. So our initial angle in this formula here, our initial angle here was 0. Okay, and then 2k plus pi over n. What we're going to do here is k is going to go from 0, 1, 2 up to 4 because we're doing the fifth roots. So we're starting with 0, right? The cosine of 0, I sine of 0, and then we're going to add 2 pi over, again, when k equals 1, 2 times pi over n, that's 5. So 2 pi over 5 would get added to it. All right, and then we would add, when k is 2, 4 pi over 5, and then 6 pi over 5. And that's going to be our ways that we make our way through this. It's just going to be rotation. All right, so there's the 2 pi over 5 with the 0 in there, 2 pi over 5 with a 1, 2 pi over 5 with a 2. So we're just adding that 2 pi over 5 over and over and over again. All right, notice our power, the fifth root of 1 is always 1. We're always going to get 1 out there to the side. And that's going to be our solutions. All right, e to the I 2 pi over 5, that's, unfortunately that's not a special angle, but that still, we could still write it in that form, an exact value. But we could also approximate it. And if you look at what happens, this is a really cool little thing mathematically that happens, is if we plot these, right, the fifth root of 5, we get like a pentagon. If we connected these with a straight line, we would get like a pentagon, a regular pentagon. So there's the only real root of 1, fifth root of 1, and then these others, this is the e to the, this is the 2 pi over 5, this is the 4 pi over 5, and notice they all have a magnitude of 1. They're all 1 unit away from the origin. All right, let's do one that has a little bit nicer numbers. So let's find the fourth roots of this complex number, -1 minus I squared root of 3. All right, so same thing. What is our magnitude? Our magnitude, if you square the real part and the imaginary part, square -1, we get 1. Square root of 3, we get 3. 1 plus 3 is 4. The square root of that is 2. All right. Negative and negative, that means we're in quadrant 3. All right, this part divided by this part would be the square root of 3 over 1. So in quadrant 3, what makes tangent equal to the square root of 3? And that's 4 pi over 3. So there's our angle. Okay, so there it is in its complex form. All right, and then if we start writing the fourth roots of that, how do we do that? We find the fourth root of 2 over and over. We start with this angle, right? We start with our 4 pi over 3. And every time that we rotate from there, every time we rotate from here, I want to show you this is the one that we would actually start with. And every time we rotate from there, this is when k is equal to 0. We add 2 pi over n. What's n in this case? N is the fourth roots. So we're going to add 2 pi over n, which is 4, right? Which is pi over 2. So if I add pi over 2 to 4 pi over 3, right, common denominator there is 6, right? So I would get 8 pi over 6 plus if I add if I get a common denominator here, it'd be 3 pi over 6. All right, 8 pi over 6 and 3 pi over 6 is 11 pi over 6. And that would give me this one. This is when k equals, starting to get a little messy here, sorry. This is when k equals 0. This is when k equals 1. Now if I add pi over 2 to 11 pi over 6, once again I have to add, I get a common denominator, that's going to be 3 pi over 6 again. And I would get 14 pi over 6, right, which reduces to 7 pi over 3, right, and that is coterminal with 1 pi over 3. How do I know that? Just remember, we can subtract, this is bigger than 2 pi. We can subtract 2 pi from that, which would be 6 pi over 3, and that would get me back to pi over 3. So this is when k is equal to 2. And then finally, if I did it one more time, I'd get k is equal to 3. And remember, that's what we do. We do 0, 1, 2, and 3 when we're finding the fourth roots. All right. So it's giving it to us in smallest angle and order of rotation to largest. But just know that we can get this in any order depending on where we start from. So this is quadrant 3, so we're starting with the third quadrant one. Fourth quadrant, first, second,